Today in SwiftUI, fluid and delicious animations. Hello Internet! Today we will finish our little saga on fixing the problems of interactive SwiftUI animations. Last time we took a look at swipe actions and some issues with that. We built a basic version of swipe actions. And today we're going to finish that and solve get all those little juicy details just right, just dialed in. But first, a brief interlude with this little example, with this little blue box floating around, just to focus and specifically pluck out some of these issues. So here we have a box that will jump between a couple of target locations, and the intended target location is determined based on the velocity of the swipe. So that's nice. But of course, the velocity of the swipe, I'm swiping really hard now, doesn't really affect the speed of the animation. So a gentle swipe and a really rough swipe does not really change the way this looks, which is a bummer. A second huge problem that we did not discuss last time, which is a big one as well, is if I drag it here to this point on the screen and release it, will jump back to the bottom because it's closer to the bottom target. However, if I release and then try to grab it again and drag it upwards, we'll see a jump, an ugly, revolting, nauseating jump in the animation. And that's all because with the built-in SwiftUI animations, it's a beautiful, brilliant implementation that works most of the time. But when you want control, specifically when doing these kinds of interactive animations, you kind of relieve a lot of that control and hand it off to the SwiftUI runtime. For instance, when I throw this upward, we'll notice the Y offset value. This is that state property, at state var Y offset. It jumps to negative 250 right away. Negative 250, despite animating the rest of the way up and down, it's sort of stuck. It jumps immediately to its target state. And then the SwiftUI runtime internally handles that nice spring animation. But if you want to use that value, for instance, when you interrupt, you want to get the current Y offset to continue animating from that position, like if I release and then drag, well, it jumped to 250. So when we start to drag again, the thing jumps to 250. The little rounded rectangle there jumps to 250. And that looks unsightly. At the end of the day, that's kind of the problem underlying all of these issues with the built-in SwiftUI animations, is that you are giving up too much control to the clever SwiftUI runtime. It's just not built to be this flexible. So we can't set a nice velocity. There are some techniques for setting a velocity. If you've ever played around with the interpolating spring, there is this initial velocity setting, but it does not work how you want it to. It's very finicky and it just doesn't really work. It's kind of a dead end. I played around with that a lot. Kind of got it to work a little bit, but it has a lot of rough edges. And this rough edge of the jumping animation is there as well. So we want to switch to something where we have full control. And that's this example, which looks the same. However, a hard swipe flies off the screen, a gentle swipe flies differently. I can now throw it off to the side and it arcs quite delicately using that inertia. Feels good. And also, if I release and then grab it again, I can interrupt it. And it just feels nice. I can just catch it. So that problem is solved. And you can even use these powers to do even fancier things. We have the velocity information and we have exactly the current offset. Notice how that Y value is constantly updating until it comes to a rest and stops animating. So this is great and looks fancy. And we can do this, unfortunately, not with the built-in SwiftUI capabilities. We'll have to turn to a third-party library, and we're going to talk about how to use that. It's called Wave. It's what I'm using. And then I might also be adding some code or maybe making a fork of Wave that's specifically for SwiftUI, because it's built mostly for UIKit, but it can be made tailor-made to work a little more nicely with SwiftUI. Okay, so that's the introduction, and we're going to take a look at these problems and then apply them to our SwiftUI swipe actions and make that feel perfect. See you then. Let us begin with this little playground for throwing a rounded rectangle around in, and it returns without any respect to the velocity of the throw as per usual. So here's a focused, constrained playground to explore these ideas before returning to swipe actions, of course, I swear. Now I wrote this code without you because it's incredibly basic. It's 20 lines or so. So we have an offset, which is just a CG size, which, if you don't know, is merely a width and height, which seems strange for representing offsets perhaps, but that's kind of how SwiftUI does it. The translation is a CG size, so we're just going to stick with their data type. I mean, whatever the name, X and Y coordinate, width, height, it works. And we're starting it out at 0. And then we have our beautiful, critically rounded rectangle, blue, 100 in each dimension. We offset this by our offset CG size, so offset can accept a CG size, and it will be offset in the X and Y coordinates according to the width and height of the size. And then we attach a gesture here, which looks similar to what we started with last episode, where we change the offset to be equal to now the whole translation. We don't need to pluck out the width because we're using the whole size. And then when we release, we are going to reset to 0 with a delicate spring animation. And it works as it says on the tin. So before we make this wonderful and allow this to actually respect velocity and give us a feeling of fluidity and impact, and also, of course, fix that idea when we try to interrupt, that it sort of jumps back to the starting point in some awful way. We'll fix both of those. But first, there is this tempting shiny bauble at the bottom of the lake, which we might be beckoned toward. And that would be the interpolating spring animation, because here we see the word velocity, which is kind of what we're going after. Velocity, we could set the initial velocity. We don't need any other special tools. This, perhaps, is our answer. So let's briefly explore why this is not at all the answer, and also understand how it works if you were ever curious. We'll give it some spring animation. I'll just do smooth. It doesn't much matter. And let's start with 0. If we start with 0, it behaves just the same as it did a moment ago. And now let us change it to 100 and see what occurs. So I will lift our rectangle into the air and release it. And it overshoots by quite a good deal, maybe hundreds even. Too much velocity. I'll make it 50. It overshoots. And now let me bury it deep down into the earth and then release the rectangle. And it overshoots its target. So when we have a positive velocity, it seems to add some oomph, a little bit of nitrous oxide to the animation, no matter which direction we release it from. So that is interesting. Let's now make it negative 50 and see what happens. And when we do this, the animation kind of bounces back away from its target before completing. So this initial velocity, the value of itself relates very much to the direction of the animation. So negative 50 isn't negative 50 units in the X or Y or Z axis. It's sort of negative 50 in the exact opposite direction of whatever values are being animated. Maybe one value, maybe multiple values, whatever you change here in this block. And this can be difficult to work with for a couple of reasons. Let us grab the value here and let's grab the velocity. So value.velocity is the CG size. And first of all, we have to just put a single double here. We cannot have this size velocity, which represents both the width and height velocities, the velocity of the Y direction and the X direction. So we have to pick one. For now, let's just pick the Y velocity. So let's see what happens when I throw up. And remember, in SwiftUI, the origin of the coordinate plane is in the top left. So a negative Y value will be higher than a positive Y value. So the Y value gets lower as you get higher. It can be a bit counterintuitive. The X is still left is negative X, right is positive X, but up is negative Y, down is positive Y. So let me throw this upwards and let's see what happens. Okay, it really throws off the screen. So let me decimate this value, grab a tenth of it, so we can actually kind of see what's happening a bit better. So yeah, there's definitely an impact on the animation. But now let me toss it downwards. I'm tossing it downwards, but it's actually shooting really quickly in the opposite direction before coming to rest in the middle. And if you remember what we just said about how initial velocity works, and think about it real hard, you'll see this makes sense, but it can be confusing. So because this can be a little confusing, let's look at some fancy line animations. So here's our rounded rectangle, and let's say we released it up here, and its target, its goal location would be beneath this outline. So this white line represents the path of the animation, and if we have an interpolating spring with a velocity of 0, it will just kind of nicely, smoothly animate along that path. If we instead bump up the velocity, it's going to overshoot its target. It'll sort of be launched rather quickly, overshoot, and then come to a rest at its goal. If we have a negative initial velocity, it will first bounce back along the animation path. So the important thing to know here is that this velocity affects the trajectory along the path of the animation, which in this case is this simple vertical line, but it could be sort of in any direction. And it can also involve depth or opacity, other properties. Anyhow, the velocity is just this one scalar value affecting that path of the animation. Similarly, if we release at the bottom and the goal is above our starting position, well, a negative velocity will actually shoot us downwards because it's going to be in reverse of the direction of the animation. So this velocity affects the path of the animation. So the same negative velocity, when our path is going from top to bottom, will shoot us upwards or shoot us downwards. The point is against the path of the animation. And similarly, if we release from beneath with a positive velocity, we will shoot above our target. Now, why this can be confusing is, say we're dragging and we release up here with a force of negative 100 in the y velocity. Quick piece of information, in SwiftUI and iOS in general, the coordinate plane, the origin of the coordinate plane is in the top left, which means negative y values means go up on the screen, positive y values means go down, negative x is to the left, positive x is to the right. So it's a bit counterintuitive. We might be used to positive y being upwards on whatever line graphs, etc., but it's slightly inverted. Our intuitions are slightly inverted. So a negative y velocity will mean that we released dragging upwards on the screen. And if we just naively take that y velocity value that we might get off of the drag gesture and apply it to our interpolating spring's initial velocity, well, that is a very different value. That is a very different meaning here. And that negative velocity will be against the path of the animation. And because the home, the destination, was above us, that negative 100 actually says jump back along the vector of the animation. So this will result in this awkward bounce back effect where we release while dragging upwards, but then immediately the rectangle will bounce backwards. So it will not feel natural at all. It will feel very awkward. This can be extra confusing because if we just happen to release above our goal, so the same exact situation, we're dragging upwards and we release, but our goal was beneath us, things will seem like they're working correctly because the path of the animation goes from above to below, and therefore a negative initial velocity will result in the rectangle jumping against the animation path, which happened to be from top to bottom. So things will look kind of okay in this situation, and it'll feel natural, like the velocity of our swinging motion was preserved through the animation. But that is merely a coincidence, because the same gesture released from beneath our target will feel very awkward. So the point is, initial velocity is relative to the path of the animation. So even if we did struggle and get the vector math to work where we could translate from our xy velocities into this initial velocity that works along the path of the animation, it is possible, it's a little difficult. Well, we're still going to have a problem because we have these multidimensional animations. So we could have also been dragging our little rectangle off to the right very hard. So there would be a high x velocity and a y velocity that's close to 0. And if we did this, we would want the animation path to arc out to the right as it gently then descended back to its origin. But we could have also had a positive velocity and a y velocity, and we would have wanted this upward arc trajectory. But if we remember, the initial velocity works along the path of the animation, which started here and is going to end here. So really, we can only decide, do we want to go more strongly along that path? Do we want to amplify that path, resulting in an overshooting? Or do we want to first bounce back before taking that path? So we can really only choose an amplitude. We can only scale along the vector of our animation, and we do not have the ability to give more fine-grained controls along this sort of multi-dimensional vector of an x velocity, a y velocity. We might also imagine that we're, using the new Apple goggles and throwing it along a z dimension as well. A lot of options, and we really cannot compress that multi-dimensional vector into this single scalar initial velocity double value that is received by the interpolating spring constructor. So yeah, we're going to abandon interpolating spring. You can have fun with it if you want. It's probably useful in certain situations, but not great when you want to make fluid animations that you have fine, full control over. Okay, so now that we have finished discrediting this tempting, yet ultimately dissatisfying interpolating spring animation, let me remove it from the code, and we're back to our usual disappointing velocityless animation. And now it's time to make things really nice, finally. First in here, and then we'll take what we've learned here back to our swipe actions. So for this, we're going to want to turn to this library called Wave, and I'll have the link to this in the comments below. And what it is basically a spring-based animation engine for iOS and macOS that makes it easy to create fluid, interruptible animations that feel great, and that's exactly what we desire. It is primarily built for UIKit, but there are definitely ways of getting it to work with SwiftUI. It might not feel as idiomatic as the built-in things. I'm hoping to perhaps open an MR, PR into this. But first, let's just see how to use it out of the box. So first I'm going to copy the URL and then jump back to Xcode, wherein I will click into here, go to the project, package dependencies, and I will add Wave. And I'll add it to swipe actions from scratch. Now we have Wave. And now I will import Wave. And so the key to getting Wave to work is that we will need to add another property to our view, this thing called an animator. So I will say offset animator. And we're going to initialize a spring animator. And this is parameterized by some type, which is the value it is animating. It doesn't work with every type, but most animatable things it will work with. So CG floats, CG sizes, I believe CG rects, and you can add your own support. But for now, we'll just look at it with CG size. And it is initialized with a spring value. And I will just start out with this default animated spring value. And so what we're going to do is, instead of ever changing our offset directly, we're going to allow the offset animator to update our offset for us. And we just adjust the offset animator's target position. So instead of ever assigning directly to offset here, we're going to say offset animator dot target and assign that instead. So offset animator dot target. We will get rid of our animation block, and I'll get rid of velocity for now as well. And there's a couple of extra steps. Instead of just being able to set the target, we also have to explicitly start our animation in both cases. And when we're dragging around, we don't actually want the normal animation, so we will set the mode equal to non-animated, and on ended, we will set it to animated. So a bit of boilerplate. This is where perhaps building a more specific SwiftUI interface can come in handy, but it's worth it either way. So now this animator, when given a target, will change some internal value towards that target in either an animated or non-animated fashion. But the question is, how do we get access to that internal value? I mean, we really want to update this offset state variable, so how do we do that? Well, this is where we're going to have an onAppear modifier, and we're going to connect the offset animator to this piece of state. So offset animator dot value changed is a value that takes a callback block to call when the animation's value changes as it executes. So we're going to want to assign this to a closure, which will take the value that has been changed, that CG size internal to the offset animator, and we can just set our own offset equal to that value. And one last thing we'll need, so things do not explode, is we'll need to set an initial value as well. So we're just going to make this the same. The train is passing. So we can just start it out as the value that we assigned here. And now let's see what happens. I will rerun my preview, pulling it over here, releasing, and it's still animating. In fact, it's behaving just as before. There's still no velocity at all, but it's working. But now we have everything in place where we can get this to work. So I can take the value from our drag gesture, and Offset Animator has a velocity property, so I can set that equal to the drag value's velocity. And then I can try it out again. And now there is a bit of response. It might be difficult to tell, but it's definitely shooting out past where I release. We might want to multiply this velocity a bit just to make it more noticeable. Unfortunately, CG Size does not have the times operator, but I can quickly add an extension. I will paste this from a secret place. So now CG Size can be multiplied by a scalar value. And now it's even more noticeable. I will make it times 4, so it really flies past where I release based on my velocity. So it's feeling good so far. Now the other really nice thing to note, if I add an overlay here and add some text, I will print the offset to the screen. And let's just print the height value. So notice how when I release, it's updating every, well, screen render. So before, when we used a with animation block, let me change that real quick. So with animation, we set offset equal to 0. And also offset equals value.translation. Let's set this back. So when we use the built-in SwiftUI animation, notice how the value jumps right back to 0. But now, because the animation, that smooth spring animation, is not done internally in SwiftUI, it's instead done by this offset animator, we have full access to that value as it changes. So we can look at it, watch it smoothly go down, but we can also use this value to interrupt our animations and grab our rectangles out of the air, interrupt them midair and drag them, which we can't quite do yet because we need to actually make use of that value. So the problem here would be, similar to the other day in the swipe actions video, we're setting our target equal to the value.translation, which is the amount of movement that has occurred within that single drag gesture. So if we grab and then drag, well, that was a second drag that started from about here, and so we're seeing the offset relative to the beginning of the drag. But we want to also take into account where the rectangle began. And we can do that quite simply by adding a couple of pieces of state. So I will say offset start, and then I will also say is dragging equals. And then I'll do a couple of things. So on ended, we'll say is dragging equals false. And then on changed, I will say if not dragging already, we'll set is dragging equal to true. And we'll set offset start equal to the current offset. And then instead of just setting the offset animator to the translation, we will add the offset start to that translation. And of course, unfortunately, there is also no plus method for CG sizes. So let's scroll down to our helper, copy this, multiply, we'll make it a plus this time. The right-hand side will be another CG size. And so instead of multiplying these together, we will add the respective widths, as well as adding the respective heights. And once I've done that, I should now be able to drag as usual, and then interrupt and grab from where I released. And it totally works and feels good. And basically that's the key to nice, interruptible, smoothly animated gestures. They can maintain their own velocity. So now that we know how to use Wave, let's get some practice by reapplying this technique to our swipe actions view. And now for our grand finale, I have copied the swipe actions view that we had at the end of last episode, prefixed it with the word fluid, and now it's just a matter of connecting Wave to it and refactoring it, taking the animation out of control of SwiftUI and into our own hands. So I'll start by saying import Wave, and then we will find our offset. We're no longer going to directly set offset. Instead, we're going to create an offset animator, which will be a spring animator of this time a CG float, because we're only controlling that X offset. We will then initialize this with just the default animated spring, And now we just have to find everywhere we modify offset. So that's going to be in our onChanged and onEnded blocks. And instead of directly modifying the offset, we will modify the offset animator's target and just change that everywhere. Then we will be sure to remove the animation blocks with animation. And we'll need to manually kick off that animator with start, doing so in a non-animated manner up here, and beneath we will do it with animation enabled. And the last step to this would be to scroll up to the body, add an onAppear modifier, and within here we'll need to connect the animator's value to our state property here. And we can do this by saying offset animator. First we'll give it a default value of whatever the starting offset was. And then we will set this onChanged closure equal to updating that offset state property to the value that changed inside of the animator. And we can just use $0 here as a shorthand. And with this in place, we still have everything working just as before. No velocity yet, but that's now a trivial solution. All we have to do is come down here to onEnded and set the offset animator's velocity equal to value velocity, except the offset animator's velocity is now a CG float because that is the type of its value. And so we will pluck out the velocity in the x-axis, the width on that CG size. And now if we do that, there is springing. As you see, if I open gently, smooth. But if I toss it here or there, it jumps, and I can make this more exaggerated by multiplying it, and we'll see that it really swings as I give it a little bit of momentum, which is pretty great. And further, we can also interrupt this animation wherever we want to and keep going. We've already basically written the code for this when we've stored off that start offset, except now this offset value is going to be exactly what is represented on the screen and not the goal state. So there won't be any jerking if we interrupt right away after the offset has been set to a very different value. Instead, this offset will always be what is represented on the screen, and the target is going to be secreted away inside of our offset animator, which we can still access if we desire, but we don't have to. So yeah, Wave is a very nice library. Highly recommend it. Hopefully this shows you how you can use it with SwiftUI. And perhaps in another episode or session, I will show how one could modify it to be a little more SwiftUI idiomatic, so you don't have to set these callbacks or deal with all of these properties. So yeah, I hope that was enjoyable, and once again, thank you for watching. Don't forget to do the swipe actions if you haven't already. I much appreciate that. And yeah, I'll make some more videos soon. All the comments have been nothing but sweet. YouTube comment sections, I think, have gotten a bad rap because I've only experienced many very friendly, nice, generous people. So thank you for all of your enthusiastic and encouraging remarks. I will make one more video in this series at least, so stay tuned. What I'd like to cover is, if we scroll down to the point of use here, this is not what it looks like when you use swipe actions with the default modifiers. Here we had to make our own special action struct and pass it in as an array in the default version, which I have here somewhere. Instead, you get to just say .swipe actions and pass in this closure, and it's not sort of inside of an array. So we can take a look at how we might achieve something like that and make this whole thing look a little more SwiftUI idiomatic, and maybe even release it as some kind of GitHub library if that would be helpful to people. That'll be fun. So see you around. Goodbye.